All right, let's take a look at how Gibbs free energy and spontaneity relates to these voltaic cells that we're talking about, or to electrochemistry. And so we'll notice our first problem here is that we've got a galvanic cell, we've got silver and copper, and here's the reaction, and we're figuring out delta G for the reaction. And so we have an equation that relates the Gibbs free energy for a standard cell, or the standard Gibbs free energy, to the standard cell potential, which we just learned how to figure out. And so delta G standard, in addition to all the other things it was equal to in the last unit, you know, the delta H minus T delta S, and you know, negative RT ln K, etc. This is also equal to negative N F E standard, and E standard being that standard cell potential we just figured out how to calculate. So the N is basically considered to be a unitless number, and this is the moles of electrons transferred in a particular redox reaction. So when we're balancing those half redox reactions, or half reactions, the oxidation and reduction parts separately, that number of electrons that we see represented on one side or the other of the equation, that's going to be where we get that number from. So in some cases, like this reaction, it's going to be pretty easy to spot what that number should be, but in other cases we can do the half reactions and figure that out. F is our Faraday's constant, which is going to be given to you. That is 96,500 coulombs per mole of electrons. So that's basically telling us the charge per mole of electrons, and so it's a constant that we're putting in here to help us convert between the units for delta G and E standard. And this, of course, is our E standard, and that is in volts. Now, the thing to remember is that volts, 1 volt is actually equal to a joule per coulomb. So you'll notice when we plug in all these things, we end up with something with coulombs divided by moles times joules per coulomb, and so we'll be left with an energy per mole unit, which is what we know delta G standard is reported in. This will be in joules, and it should be a very large number though, so we'll probably be putting delta G back into kilojoules, but we'll see that in a minute. Okay, so for this reaction, again, we want to find the E standard for the cell potential. And so again, we've got silver, which is going from +1 to 0. So silver is being reduced. And then we've got the copper going from 0 to +2. And so copper is being oxidized. And so we're going to look on our table here. So the thing that's reduced, again, that's going to be at the, let's see here, anox red cat. So this is at the cathode. So we're going to write that one first, and we're looking for its reduction potential just as is, so that's 0.80 volts. And then again, whether you're subtracting off the value for the reduction potential at the anode, or if you're just changing the sign for the reduction potential. So this is you know, going to be subtracting off the value as it appears on the reduction table. So this is copper going to copper +2, so we need to make sure we look at the right one. So this is the copper +2 converting to copper, so that's the reverse of what we have there. So again, we're going to take this 0.34 and putting that there, and so then our difference will be 0.46, and that's volts. And again, the volts unit is the same thing as a joule per coulomb. All right, so now we're just plugging in. Well, actually, before we plug in, we got to figure out what N is. So notice that for every, well, actually you can kind of see it on here. You know, we've got silver. Each of these silvers to convert to the silver in elemental form is gaining 1 electron, and the copper is going to be losing 1 electron if it's the reverse reaction as the oxidation. So you'll notice that with this silver, with the 2 in front of it, basically this is gaining 2 electrons and the copper is losing 2. So that's going to be N equals 2 value. So delta G standard equals -2 times the 96,500, and again that is coulombs per mole, and then times the 0.46, and I'm just going to write in the units of what volts equivalent to so I can see the units and what they end up being. So if I multiply all that out, I end up with -88,780 joules, and again I would convert that to kilojoules dividing by 1000, and that would actually then keep two significant figures limited by this one. This is an exact number. So that's negative 89 kilojoules per mole of reaction as written. That would be my delta G standard for this particular reaction. I can't see my answer on the sheet. Move it over. There you go. So that means that this is spontaneous, right? So remember, delta G being negative means it's spontaneous. We also know that the E standard for the cell, when that's positive, that means that it's spontaneous as written. And since this was positive, you know, we could already tell this is going to be a spontaneous process as written in the forward direction. And again, we can see that, well, when this is positive, obviously with this negative sign in here, that's what makes this end up being negative. And again, we see a negative delta G for that same spontaneous process.